Welcome to the third episode of the RC Test Flight Propeller Design Competition. In this episode, we're going to test 8 more propellers and then reveal the winner. And we'll also test the noise levels of a few of the propellers to see which ones are quietest underwater. But wait, there's more. We also have a handful of bonus propellers to try out. So let's get started and meet our first 8 contestants. Here we are. The first one is Prantle DAE, which was submitted by APA 609. He says that this propeller was actually based on the design of a human-powered aircraft propeller and is optimized in the computer program X-Rotor. It's optimized for a speed of 3.5 meters per second at 1700 RPM, and he's using the Prantle BSDM span loading strategy to hopefully prevent the blades from breaking. Basically what that means is the root of the blade is supposed to make the most thrust, and then as we get towards the tips, the thrust tapers off, so the tips are basically making no thrust at all. And that's so that the majority of the force is in here where it's strongest, and you don't have as much force where the lever arm is the biggest and you're most likely to snap the blade. So like all the other high aspect ratio propellers, this will probably do pretty well because the blade should have a higher lift to drag ratio, or at least in theory. APA 609 has a confidence level of 5 out of 10. That's not very high. I have a higher confidence level than he does. Next we have Screw It, and it was submitted by Toon Verbruggen. It uses custom airfoils that were modified from another human-powered aircraft airfoil. Interesting. He said that he used CFD to fine-tune the blades, but then said it's a rushed design, but it should be good enough. I don't know what good enough means, but its confidence level is 8 out of 10. My thoughts on this propeller is that the blades are like a narrower aspect ratio than the baseline propeller, which should be good. The diameter is slightly larger, so I would guess it performs very similarly to the baseline propeller, if not slightly better due to the narrower but longer blades. Okay, here we go for some funky ones. This one is called Probably Alright, and it was submitted by Dr. Dinkle. I would have called this the squid head. He says he's no engineer, but it will be a sight to behold. The process of deciding the dimensions could be compared to rolling the dice, and his confidence level is only 2 out of 10. My thoughts are that, it's gonna be more of a blender than anything. The angle of attack of the blade down here is basically vertical, so it's just gonna be flinging the water out like an impeller. I don't think this is gonna do well at all, but you never know. Next up, we have the Peter Piper picked a peck of pickled God damn it. Peter Piper picked a peck of pickled propellers, and it was submitted by Silas. He says this design utilized a lot of the data from the intro video, and that the end of the hub is more gradual to prevent the stagnation zone that we were talking about before. His confidence level is 7 out of 10. Due to how these propellers are printed, I required everyone to have a hole in the tip to prevent cupping when it's going up and down into the resin tray, but he didn't want to do that, so he designed a separate screw-on tip. And I printed it and then tried to screw it on, and it didn't fit. And then I checked the CAD, and it turns out that the threads are not even the same pitch. And the inner thread is also a larger diameter, so there's no physical way that it would fit inside. So Silas, you need to work on your thread design skills. I just ended up drilling it out and then shoving the tip in there, and it just stays by friction. So my thoughts for this propeller is that it's probably going to do decently well because it's like about the same size as the baseline propeller, but just more streamlined. So can't go wrong with that. Next up, we have More Blade, Less Blades, and it was submitted by Matt H. His rationale for this design is that leading edges and trailing edges cause resistance, so by increasing the blade area, we have less drag for the same amount of water displacement. His confidence level is a solid 9 out of 10. After printing this propeller, I noticed that there's also kind of like a cupped trailing edge, so that should be interesting. I kind of disagree with his theories about leading and trailing edges causing drag. Yeah, I think this propeller will do like worse than the baseline propeller, but it'll push the boat, that's for sure. This is Spin It Like You're In It to Win It, and it was submitted by Tomas Roznikek. He said that he used CFD to design this propeller and said it took over 800 CPU hours. His theory is that since efficient airplane wings are long and thin, the same concept must apply to propellers. He went with 2 blades rather than 3 because it would allow him to make the blades longer with the same amount of drag. He also increased the blade thickness to hopefully prevent them from snapping, and his confidence level is 7 out of 10. My thoughts are that, snapping is definitely a concern. If I push on it, the blades definitely flex a bit, but also, like looking at the airfoil, It's a pretty thick airfoil. Like, it's not super thin. It's actually probably thicker than a lot of the other props. The airfoil at the root is pretty thick too. But I think there's also a big downside to having a thick airfoil with a thin cord. But maybe these super narrow blades are extra efficient. Not sure. It'll be interesting to see how this does. Next we have Contender 25, and it was submitted by Contrail 52. This is a crazy coincidence because it was the 52nd submission, and 25 is 52 backwards. And he said Contender 25 was the 25th case that was run out of 35 total CFD iterations. He also said that he tried adding vortex generators to the upper surface, but they only made the performance worse. So he got rid of those. The open foam simulations took 43 hours with his 16 core CPU. His confidence level is 10 out of 10. Nice. I don't think it's gonna, where'd my baseline propeller go? I don't think it's gonna do all that much better than the baseline propeller. The blades are kind of cupped, like they have a lot of antihedral. So that's interesting. Yeah, I bet it'll probably outperform the baseline propeller considering that I did 0 CFD. Also, yeah, the span is a little bit longer and the root cord is a little bit narrower. So I bet it would outperform the baseline propeller by a little bit, but we shall see. Next up is the Bionic prop, and this is basically like the one called Nodules and Feathers from the first video, but this one doesn't have the feathers. It only has the, what are those things called? Tubercles. So this is kind of like isolating the variables. We'll see if the tubercles alone help or hurt the performance of the propeller. But other than the tubercles, it's identical to the baseline. This one is called Fibonacci's Golden Ratio Propeller. The blades are super thin, or the whatever you call these things, the flaps are super thin, like you can almost see through them. So I was suspicious that this one would break. O&S designed and submitted a variable pitch version of the baseline propeller. Basically, when you push on the blades, the pitch changes. So the idea was that at higher RPMs and at higher speeds, the blades would have a higher pitch. I told him that he had to print and assemble this propeller himself because surely this design was going to take a few iterations to get the mechanics right. So that's what he did. That's it for all the introductions. Let's start off our testing with probably alright, maybe. In the bubble view, we can see that everything is stalled. There's flow separation everywhere, and the bubbles just get blended. This propeller didn't even make it up to the 2 meter per second starting speed, which means we can't even really rank it against the rest of the propellers. Next up is Screw It. In the bubble view, we can see some flow separation at the tips, which is a bad sign, but that mostly seems to go away at higher RPM. It also occasionally looks like the entire blade is stalled, which suggests the angle of attack is slightly too high for the speed range it's operating at. But keep in mind, this underwater camera is not attached to the boat during the actual efficiency test. I only attach it for filming afterwards. It increases the hull drag quite a bit, which reduces the speed of the boat, so a prop that appears to be stalled here might not actually be stalled during the data collection. Screw It scored an integral efficiency of 21.5, which is about 10% worse than the baseline propeller. Next, it's time for Prantle DAE. The bubble view for this prop is actually quite interesting. There are 0 of the helix vortices that we see with most other propellers. This is a strong sign that the Prantle span loading strategy reduces the strength of the vortices, or distributes them over a larger area. If this is true, it should also reduce the induced drag of the propeller. We do still see some vortex action happening down here with this last line of bubbles. It gets wrapped around the vortex into this wave pattern. Prantle DAE scored an average integral efficiency of 31.3, which is 40% better than the baseline propeller. Later in this video, we'll find out how it compares to Span Maxing, which is the first place contender from the first 2 episodes. By the way, if you're confused by any of this, I'd highly recommend going back and watching the previous 2 test videos, because I cover a lot of things that I'm leaving out of this video. How much are these, like $1,000?
This 1,006, I got it for cheap.
Oh yeah? Used?
New one in the box, I got it for 100.
Now it's time for Peter Piper Picked a Peck of Pickled Propellers. This propeller looks pretty normal, although it is a bit surprising that the pointed tip doesn't really appear to prevent flow separation at the end of the hub, or the stagnation zone, whatever you want to call it. This propeller scored an average integral efficiency of 23.8, which is around 7% better than the baseline propeller. How'd you do that?
My old brother, he wasn't need money. One day he wasn't here. No, how do I need money? I said, what do you want me to do? He said, no, I have new drone at home. I said, bring it, I buy it. How much? They tell price. I say, no, I can't give you this too much money. If you want, I can give you 400. He tell me, you crazy, man.
Good deal for you.
Yeah.
Next up is More Blade, Less Blades. This propeller has some big, thick vortices, which is not a great sign, but there isn't any obvious flow separation from the blades themselves, even on the cupped trailing edges, so that's good. More blade, less blades ended up scoring an average integral efficiency of 18.5, which is roughly 17% worse than the baseline propeller. This goes to show that Matt H's theory about the leading and trailing edges causing resistance is most likely incorrect. It's the blade's wetted area that matters more, and this prop has too much of it.
Look at this dude. He's going out on every pier. Just jumped a rogue wake.
So you might be wondering, why bother with all this testing in the first place? My friends, now you know why. And I'd like to take this opportunity to thank the sponsor of today's video, which is ShipStation. I've been a ShipStation customer for years. I used them during the Snowcat project for shipping out all the Snowcat kits, and I also use them for Stratus LEDs, which is like high-powered drone lights and stuff like that. We actually used one of the Stratus LED modules to light the propellers for the underwater shots, if you remember back to the first video. But ShipStation is a service that streamlines the shipping and order fulfillment part of your business, and I would highly recommend checking them out. Here's why. If you're selling physical products online, you have a lot of things to deal with. Fulfilling orders is no simple task. You have to deal with addresses, inventory, postal rates, package sizes, and all sorts of other headaches. So wouldn't it be nice if there was a service that would combine all this stuff into one easy-to-use program? Well, thank goodness there is. ShipStation even has features that make business reporting and customer service much easier. The first step to using ShipStation is to import all your orders. Luckily, ShipStation is integrated with dozens of the most popular selling channels, so all you have to do is connect your web store and let the orders start flowing in. ShipStation saves me money because it allows me to effortlessly compare rates from different carriers and choose the ones that are either cheapest or fastest, depending on what the customer needs. Then once I've purchased labels for all the orders in the queue, printing them just takes a few clicks. With ShipStation, you can get industry-leading carrier discounts, so you can be sure you're never overpaying for postage. Work less and ship more with ShipStation, the innovative tool that helps turn your shipping challenges into opportunities for growth. Go to shipstation.com/rctestflight to sign up for your free 60-day trial. That's shipstation.com/rctestflight.
Oh, it's Apple. They got some LiDARs going on there. Oh, big waves.
Next up is spin it like you're in it to win it. This propeller was visibly bending, so we're lucky it didn't break. One interesting thing is that there's no trail of bubbles clinging onto the back of the hub like we see with most other propellers. I'm guessing this is because the blades of this propeller have very little twist, so most of the thrust is coming from the tips. For this reason, the flow going around the hub is slower and less turbulent, so it stays attached more easily. Spin it like you're in it to win it scored an average integral efficiency of 29.7, which puts it in second place. The final score is from 3 test runs averaged together, but these graphs are just from one single test run, so that's why it's in first place here, but it's actually in second place. I should have picked a different test run to use for this graph, but whatever. Oh, it's not. There's not a. That's the USB-C port.
Oh shit.
Next up, we have Contender 25. The bubble view doesn't show anything too out of the ordinary. The vortices are relatively small, which is good. No signs of flow separation on the blades, which is also good. Contender 25 ended up with an average integral efficiency of 27.65, which puts it in third place. But it did have an impressive top speed of 3.63 meters per second, which is the fastest prop so far, for episode 3 at least. That's pretty impressive considering that the diameter of this prop isn't much bigger than the baseline propeller.
Ah, there you go. Thank you.
32 gigabytes. It's my first, my only drone shots for this video.
Oh yeah?
Yeah, I have no others. Now it's time for Bionic prop. Will the tubercles make it better than the baseline? The bubble view footage got messed up because the GoPro's auto exposure was out of whack, but it looks very similar to the baseline. The average integral efficiency was 21.9, which is like 2% worse than the baseline. So I don't think the tubercles are helpful in this application. Maybe they would be helpful in a different speed regime. Who knows? Next up is Fibonacci's golden ratio propeller. As you can see, it broke, but the boat still made it through the course, so we have some data to look at. It seems like if it would not have broken, it would have done just a little bit worse than more blade, less blades. Next up is the variable pitch prop.
It's really sticky, so I'm not actually sure that the water will actuate it.
I'm going to do a quick full throttle run up to see if this propeller can survive the torque. Yeah, it's not. Oh, nope, it blew up.
Oh, look at what we have here. We got a dental flosser and a prop blade.
So sad.
Somehow, a bird took a massive shit on my back, and then of course I didn't realize it and sat down.
So here are all our contestants from episode 3, plus Span Maxing from episode 2. So, Span Maxing has successfully defended its first place position. After all the testing, I went back to go look at the winning Onshape model again, and Span Maxing had gained some weight.
I emailed Austin, the creator, about this, and he said that he went in and increased the cord length right after he submitted the first version, just because he thought the deeper cord would perform better. But by the time he did this, I had already downloaded the first version, so that's what I ended up printing and testing. Since the skinny version was in first place, I decided it would be interesting to print and test the wide version as well. The bubble view looks pretty good. There's some vortex action, but it isn't too bad. No flow separation or anything like that. But man alive, that last line of bubbles getting wrapped up in the vortex is just gorgeous. I mean, just look at it. It's so beautiful, like a symphony for my eyes. And the waves are so consistent. Here the camera accidentally shifted a bit, which gives us an interesting new perspective. Kinda cool to see. Air leaking out of the mast gives us a second bubble view. You can see those bubbles getting wrapped around the vortices too. So Spanmaxing Wide Boy did not do as well as the original Spanmaxing. Its performance was really close to Prandtl DAE, and spin it like you're in it to win it. This graph shows the top 9 contestants from all 3 episodes. You can pause the video and take a closer look at that if you want. And I wanted to give a quick reminder that all of these propeller designs are available for you to download from the Onshape link in the description. Onshape is a free, cloud-based CAD program which makes sharing files a breeze. You can also download the hub for this motor so that you can print it and use it yourself. Just know that if you use any of these props on a different motor, they probably won't be nearly as efficient unless you change the size to match the exact motor specs. Now it's time to reveal the final winners for Season 1 of the RC Test Flight Propeller Design Competition. Drum roll, please. And the winner is the APC Propeller Company. The APC 6.5 by 5.5 scored an average integral efficiency of 49.7, which is 34% better than Spanmaxing and 124% better than the baseline propeller. In other words, they blow the competition out of the water. None of the 3D printed props even come close to these things. I purchased and tested a bunch of different sizes of these APC model airplane propellers to find the best size to match the RPM and speed we're operating at, and the 6 inches of medium pitch did the best. I think these propellers are injection molded glass fiber reinforced nylon. This makes them a good bit stronger than the 3D printed blades, so for this reason they can get away with being thinner and having sharper trailing edges. Both of these traits are good for efficiency, and it shows in the numbers. We're getting pretty close to the limits of what this material can handle though. I had this happen with one of the 5-inch props I was testing.
Oh god, I hear vibration. Let's see what we're dealing with.
Yeah, no wonder it took so long to get home. That's a little propeller. Just these super thin blades just can't hang.
In the bubble view, we can see that the helix tip vortices are still visible, so this goes to show that eliminating those is not necessarily a sign that the prop will be a good performer. There's no stagnation zone behind the hub, which is probably because the hub tapers into a point pretty gradually, and the blades start further in towards the center, so it's producing thrust closer to the center. One thing that kind of surprised me is that the blades occasionally look like they're completely stalled. When there's a sudden explosion of little tiny bubbles like this, it's most likely caused by the pressure on the backside of the blade dropping so low that a larger bubble will get sucked in and just torn apart as it propagates along the length of the blade. And that results in the sort of bubble mist you see here. It could also be water vapor from real cavitation, but I think that's less likely due to the fact that it only seems to happen when other bubbles are present. Also keep in mind that the camera is increasing the hull drag, which is reducing the speed, which probably makes the blade pitch too high for this specific case, which is probably why it's stalling. I feel like this wouldn't be happening without the camera on board. So the high aspect ratio airplane propellers are the clear winners, but that was kind of a joke. They're not actually part of the competition since the injection molded nylon gives them an unfair advantage over all the 3D printed propellers, and no one actually submitted them. I just tested them out of my own curiosity. So our official winner of the RC Test Flight Propeller Design Competition is, drumroll again please, Spanmaxing. Congratulations, Austin Emmons. You win a $300 coupon to PCBWay. The second place winner is Bigger Diameter is Better by Nerd1000, and the third place winner is Prandtl DAE by APPA609. They get $200 and $100 to PCBWay respectively. Now it's time to test some bonus propellers, and one of them might even beat Spanmaxing. These are propellers that were either submitted late or didn't qualify for the actual competition. First up is the Brackish to Chrome Surface Propeller by John Harris. This propeller is somewhat similar to the other spiral propellers I've tested, but I decided to test this one because it seems like it might be closer to the optimal size for this motor, whereas the other ones seemed too big. John's confidence level is 8 out of 10. From the bubble view, we can see this propeller is actually still creating the helix vortices coming off the tips. I didn't expect this, since the tips basically just run the entire length of the propeller, but it seems like the vortices just kind of start at the spot with the widest diameter.
The brackish to chrome surface propeller did quite a bit worse than the baseline propeller. For all these bonus propellers, I'm testing them against span maxing and the baseline propeller to give us a reference point. The next 4 propellers are designed by Austin Holbrook from Holbrook Aerospace. I used the Holbrook Aerospace Onshape propeller template to design the baseline propeller. Austin did a bunch of computer-aided airfoil simulations and used the program QProp to design these crazy-looking things. One has forward-swept blades and the other has backward-swept blades. I looked at these and said, there's no way. The angle of attack at the root is literally almost 90 degrees, but Austin said, the computer said, that these props would work, so I agreed to print them and test them. All these bonus props are printed on the new Formlabs Form 4 Plus with gray V5 resin. I tested both these propellers on the boat. This is the backward swept version. From the bubble view, it appears the root of the blade has some flow separation, but don't let that get your hopes down, because remember, the APC props showed some signs of stall too. But the fact that there's a constant flow of blended bubbles coming out the back did make me feel a little suspicious. Next up is the forward swept version, and this one appeared to have even more blended prop wash. There was quite clearly flow separation at the root for the entire time. So, both of these propellers did quite poorly. The forward swept version that showed the most flow separation on the underwater camera performed the worst, as expected. Shortly after Austin submitted those 2 props, he submitted 2 more with a larger diameter. Similarly to the previous 2, this one had a near vertical angle of attack at the root, and he really went out on a limb claiming a 12 out of 10 confidence level with this one. But again, the computer said it would work. In the underwater view, there's obviously flow separation at the root, but the tips look great. Nothing wrong with the tips, that's for sure. Then the boat collided with a giant patch of lakeweed and Ziploc bags. So it was time to bust out the rescue paddleboard.
What a drag. That's a lot of seaweed. Look at this mess. Looks like Chewbacca.
The second, larger diameter version had a more reasonable angle of attack at the root, but it was still steeper than usual. I was very suspicious of the previous 3 versions, but I thought this 4th one could perform quite well. The underwater view was very clean. In fact, it was quite gorgeous if I would say so myself. You can really see the swirls at the bottom wrapping forward towards the camera just as they roll around the vortex core. Just magnificent. So this propeller looks amazing, but will it beat span maxing? The answer is not quite. But it didn't do bad, and it definitely beat the baseline. The previous version with the steep pitch at the root did significantly worse than the baseline, but kudos to Austin for testing out these bold new designs. Next up, we have more propellers from the Friendship Systems and Airshaper collab. Both of these companies make software relating to fluid dynamics simulations. In the previous video, they used a surrogate-based machine learning model to create an efficient toroidal propeller with the goal of beating the other 2 toroidal propellers that I had previously tested. And they were successful in achieving that goal, but I had a hunch that their propeller was still a bit too large to be an optimal match for the electric motor we're using here. I thought this because compared to the other props, it required a bit more torque, and it was spinning at a lower RPM to meet the 400 watt power limit that all these props are tested at. I was curious if a slightly smaller version would perform better, so I asked them to send over 2 versions with 5mm and 10mm smaller diameters, and they did, so I printed them and tested them. My first impression was that all 3 felt pretty much identical, and the underwater footage shows the same. When we look at the data, it's clear my hunch was wrong. The original larger version was slightly more efficient than the smaller versions. I'll be darned. Friendship Systems and Airshaper were quite happy that their toroidal propeller had beat the original 2 toroidal propellers, but we all agreed that even the most highly engineered toroidal propeller was just not going to have a chance at beating a well-designed regular propeller. They wanted to take a crack at designing a normal propeller to see if they could beat span maxing, and this is what they came up with. The blades are quite long and slender with some sweep to them. The diameter of this propeller is 189mm, which is technically bigger than the maximum allowed diameter for the competition. For comparison, span maxing's diameter is 9mm smaller. But since I switched from the Form 3 Plus to the new and larger Form 4, I was able to print it. And now it's time for our final efficiency test. The bubble view looks very clean. The helical vortices don't appear until well behind the propeller, and there's no stagnation zone behind the hub. The blades themselves look quite clean with no signs of flow separation or stall. I was definitely a bit concerned that these blades would break since they're so long and narrow. If we look at the prop out of the water, you can see the blades have some antihedral to them, or rake as they call it in the propeller world. But when the prop is underway, the blades appear to have less rake, so I think this goes to show they are bending quite a bit, but luckily they didn't break. So now to answer the big question, will this highly engineered, machine learning and CFD optimized propeller beat our previous winner, span maxing? The answer is, drum roll for the 3rd time please. Yes, this propeller beat span maxing by 7%. That's quite impressive. Now let's throw in the APC injection molded airplane propeller. It's still quite a bit better than even the best performing 3D printed propeller. No surprises there. And here's the final episode 3 bonus propeller ranking. Pause the video if you want to look more closely. So now it's time to measure how noisy some of these propellers are. I'm doing this because whales and other marine life hate noisy propellers. But first, I want to take a shot at answering a question that I think a lot of people will have. And that is, if these high aspect ratio airplane propellers are so much more efficient, then why don't all boat propellers look like airplane propellers? I think there are kind of 2 reasons. The first is material strength. My motor here has its maximum power artificially capped at 400 watts, so that each of these propellers gets the same amount of power put into it. I'm fairly confident that if I were to increase the power limit to like 2000 watts, these airplane propellers would all just snap. Whereas these more conventional looking propellers would probably handle the power just fine. Even if you were making high aspect ratio ship propellers out of the strongest materials known to man, I think you'd eventually run into strength limitations when you start putting huge amounts of power into them. The width and thickness of a normal boat propeller blade just makes it so much stronger, even if it's being made out of inferior materials. So normal boat propellers can handle a wider range of power without breaking. And that's very important, because most people want to be able to drive their boats both slow and fast. I do think you could slap a big airplane prop like this on any old boat and increase the efficiency quite a bit, but only below like say 20% throttle. At higher throttle levels it would just break. The next reason is size. It would be pretty inconvenient for shipbuilders to have to accommodate super long thin propellers. This would make the ship have a deeper draft, which would limit the areas in which it can operate. Shallow water would get sketchy, and also, with a lot of these big ships, it seems the designers tried to make it so that the propellers don't stick down any deeper than the deepest part of the hull. This is to protect the propeller from striking objects underwater. So if you were to use a larger diameter propeller, you're going to need a deeper hull to protect it, and deeper hulls are less efficient, so that might erase any efficiency you gained with a larger propeller in the first place. I'm adding one more reason, and that is cavitation. A larger diameter propeller has a higher tip speed, which makes the problem of cavitation much more difficult to deal with. Okay, so moving on to our noise test. I've got this contact microphone here. It's waterproof, so I'm going to put it in the water and measure the noise of the propellers. This is for phantom power, and then here's our audio recorder. Okay, we're rolling. I'm starting with propeller 52. Here we go. Okay, that's that. Moving to number 6. Now for the baseline propeller. Now the 14 whale feather propeller. Toroidal propeller. It's quiet. Here's the APC propeller. Oh yeah, it's so loud. Oh my god. Wow, that's incredible how different they all are. It must be cavitation, but I can't see any bubbles coming off the prop. Like, there's no visual sign of cavitation. That's full throttle right there. So this experiment shows that if you put 400 watts of power into the motor, it results in a lot of noise with the APC airplane propeller, and not a lot of noise with the toroidal propeller. But this test was just measuring the noise at full throttle, which is 400 watts for each prop. So it's measuring noise per power, but we should really be measuring noise per thrust. Like, sure, the APC propeller is making a lot more noise here, but it's also doing way more work. So the fact that it's making more noise isn't really all that surprising. And the decibels are logarithmic, so that makes it really hard to just normalize for efficiency. For that reason, this test was pretty useless. So we got to do it again. This time I'm going to look at the data from the load cell and measure the noise from each prop at exactly 5 kilograms of thrust. That way the comparison is equal. So here's our results. I was actually pretty surprised to see that there's not really any correlation between efficiency and noise. But, this test is only looking at static thrust, so the results could be entirely different when the boat is actually moving. It's just really hard to measure noise while the boat is moving. And you would also need to control for speed, which can be tricky. Another interesting thing I noticed is that the APC propeller made much less static thrust than a lot of the other propellers. So this goes to show the range of speeds it's efficient at is much narrower than a lot of the other thicker cord propellers. I was curious if this insanely loud cavitation we're hearing from the APC propeller is at all visible. So I stuck a GoPro in the water again with no bubbles this time. This is while the boat is moving at speed. If you look closely enough, you can see a slight amount of cavitation coming off the tips. This might be the first time we've ever seen real cavitation. Everything we've seen before is most likely just bubbles hitting a low pressure pocket and just getting expanded out or torn apart. It gets even crazier with static thrust. The cavitation can be seen clear as day, and there appears to be some sort of vapor mist coming off of it. Maybe it's thousands of tiny cavitation pockets, not sure, but anyhow, it's super cool that we're finally able to see this. It's exactly what was making so much noise in the underwater audio. The fact that there's so much more cavitation visible during static thrust than there is at speed makes me think that the props are quieter when the boat is actually moving.
Good luck, fishermen. Those fish are gonna be gone once they hear this thing. So I got the underwater microphone going again, and now I'm gonna measure the dynamic sound as the boat goes by at full throttle, rather than just static thrust sound.
So this was a pretty bad test for a lot of reasons, including that I was running the boat at a consistent power rather than a consistent speed. But anyhow, the results are the same as the previous test. There's really no correlation between noise and efficiency, so that's great. It means it is possible to make propellers that are both quieter for the whales and more efficient to burn less energy. Although I'm pretty sure that when you're talking about large-scale props, it becomes really hard to prevent cavitation because the tip speed is so high. So I really have no clue if my test results can be projected onto larger scale propellers. Probably not. I'm sure a lot of you are wondering why this propeller is so much more noisy than this propeller, even though they have roughly similar efficiencies. I really have no idea. If I were to take a guess though, it's because the APC prop is probably spinning at a higher RPM, so the blades are moving faster through the water. And the shorter cord length gives the water less time to accelerate over the top of the blade, so the pressure drops lower.
Ooh. Ow, ow, rope burn on my toes. Wow, why am I turning? Okay. I need to adjust my center of thrust here. The center, what is it called? Center of effort. Wow, this is not going very well. Yeah. It's safe to say I have almost no control authority. Oh, that's too far. That's backwards. Don't go backwards. Oh my God, this is the most incapable vessel I've ever been on. Let me try and get a little more buoyancy going here. Oh yeah, okay. Oh, no, that's bad. So I'm being pulled very ineffectively by the test boat, and it's using one of the propellers from the competition, specifically the Friendship Systems and Airshaper toroidal propeller. I didn't really choose this one for any specific reason, it's just what was on the boat. You might be thinking, wow, what an efficient means of transportation Daniel is using right now. And I would argue that this is actually very inefficient, not because, well, okay, I guess it is partially because I'm on this very incapable vessel here. But the point I'm trying to make is that now this propeller is operating outside of the speed regime it's designed for. So even the most efficient propeller from the contest is going to do relatively poorly in this context. For something like this tugboat application, you're going to want a propeller that's optimized for like static thrust, basically. And that would look like a propeller with much lower pitched blades, maybe a higher number of blades. But yeah, what I'm kind of getting at here is that when it comes to propeller design, like you kind of have to aim for one target, and then the propeller is going to be pretty suboptimal for like every other application. And that's kind of one of the reasons why boat propellers are short and stubby like they are, is because if you, like we talked about earlier, if you used a high aspect ratio airplane type propeller, it's going to be great at low speed, but then just break at high speed. So unfortunately, there's just not really a one size fits all best propeller. I know what you're thinking. A variable pitch propeller would definitely be better, no doubt. But when it comes to like marine applications, there's very few boats that need to operate efficiently over a wide speed range. Like I guess a leisure craft would probably be the best example of that. But when it comes to like shipping or ferries, they just need to operate efficiently at one speed. A tugboat might actually be a good example of a vessel that needs to operate over a wider speed range efficiently. But for most boats, a variable pitch propeller would probably be kind of overkill. And it's also really difficult because designing something that lives underwater all the time and has all the mechanics to do variable pitch is kind of tricky. So yeah, what else are we going to talk about? I'm peeing. Oh my God, go straight. So we should probably talk about what we learned from this competition. I learned so much.
All those propeller test videos I made last summer are like embarrassing now. So I think the biggest takeaway for most people is going to be that a high aspect ratio airplane type propeller is more efficient on low speed boats than a typical boat propeller, or at least a propeller that looks more like a normal boat propeller, you know what I mean? I would say the biggest takeaway for me is just how insanely important it is to match the propeller to the motor. Like, I didn't realize just how important it is to have the motor operating at its peak efficiency. Like, that motor efficiency curve we were looking at in the last episode is like really, really important. I knew it was important, but I kind of underestimated its importance. Like, you can have a really efficient prop, but if you're just off the most efficient point on this motor efficiency curve, then it's just going to be an inefficient system. So in this competition, I was measuring efficiency as grams of thrust per watt. While this is a valid measurement of efficiency, what it's really doing is measuring the efficiency of the entire system, including the motor and the boat. So this was really not a competition about designing the best propeller. This was a competition about designing the best propeller for my motor and my boat, if that makes any sense. Like, we were looking at system-level efficiency of the entire boat. But I've been told by some nautical engineers that there are other ways of measuring propeller efficiency that remove the motor and the boat from the equation, so that you're actually only looking at the efficiency of the propeller itself. So I'm gonna do some testing and investigate those methods for future RC test flight propeller design competitions. But for now, I'm gonna be done with this propeller competition stuff because I got other projects to work on. And also, the lake is kind of less optimal for testing propellers in the summer. Like, there's more lakeweed, there's more boat wakes. I mean, I guess right now it's kind of perfect. But the seaweed is a problem because, or lakeweed, whatever. It's definitely a problem because the props get all tangled up and I don't really have a great way of knowing until I look at the data. So yeah, I probably won't do another prop test competition until next year. Okay, let's reel this in so you guys can take a look at the propulsion. Oh god, oh god, oh god. Now the line is tangled in the, oh my god, that's a big problem. Fuck. Transmitter stick is too loose. It just moves all over the place by itself. This is so dumb. Why am I doing this? Oh yeah, not so good. Be gone. No, 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 stop, 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 stop. So this is what it looks like from the cockpit. The hardest part is staying pointed straight. Good stuff though. I would highly recommend everyone build themselves a remote controlled tugboat to get pulled around the lake by. Although you might want to choose a better vessel than this one. I need a paddleboard or a kayak. Actually, that's how this boat started its life. Oh god, seaweed. Oh no, I don't like it. Yeah, I built this boat to be a autonomous solar powered tugboat. You guys remember that? That was like 3-4 years ago maybe. And I went like 20 miles on that one day. That was pretty sweet. Okay, that's enough for one video. I'll catch you guys later. Thanks for watching. Bye.
Blend a mission, R2 rover, so many waypoints all in order. Flip it into auto mode and off Daniel did go. GPS will lead the way from dusk to dawn, he'll sail all day. Batteries charged by the sun, until the night falls it will run. LIFEPO4, the best batteries that ever were. 10 amp hour capacity and 6 of them in store. As he ventured through Seattle, both propellers sure did rattle. You won't believe me when I say it didn't even matter.